Hello, everyone. We're working through Chapter 12, Part 2, An Introduction to Statistical Methods and Data Analysis by Ott and Longnecker. We're going to be reviewing multiple linear regression, inference for parameters. All right, first things. We're going to be estimating the residual standard deviation with S epsilon. Remember that for simple linear regression, S epsilon is found by taking the square root of SSE over n minus 2. In this case, we have the model y equals beta 0 plus beta 1 x1 plus epsilon. All right, so in this case, we only have two things that we're estimating. That's where we get the n minus 2. We have the slope and an intercept. But in multiple linear regression, we have y equals beta 0 plus beta 1 x1 all the way down to beta k xk plus epsilon. So in this case, we have k plus 1 things that we're estimating. We have the k slopes, we have k slopes involved, and we have one y-intercept. Okay, those are all the things that we're estimating. So we have k plus 1 things that we're estimating. So our equations become the S epsilon or sigma hat. The residual standard deviation is the square root of SSE over n minus parentheses k plus 1 close parentheses. All right, our degrees of freedom is equal to that n minus k plus 1, where n is the sample size. Right? K is the number of predictors. Okay, and so k plus 1 is the number of coefficients, right? All right, remember the empirical rule is that all our residuals should lie within 1, 2, and 3, excuse me, standard deviations. That's 68, 95, 99.7. So our S epsilon will give us a measure of what we think typical residuals should lie within. Okay. Remember that we have the distribution of our slope from the simple linear regression model, follows a t distribution. Excuse me. With n minus 2 degrees of freedom, but once again, those two is just the beta 0 and beta 1. Whereas now we have beta 0 all the way up to beta k, so our degrees of freedom is going to be affected. All right, so when we have a simple linear regression model, we have our beta hat following a t distribution, which is similar to the normal, remember, but it has fatter tails than a normal distribution. So if we had our regular normal distribution, then our t distribution would have fatter tails. It wouldn't come up as high, and it would have fatter tails again. And depending on the degrees of freedom, as our sample size increases, the t distribution looks more and more like the normal distribution. But we can essentially get the distribution of any of our slope coefficients. It's also going to be a t distribution with the expected value of the estimated slope being equal to the true slope. And the standard error of the estimated slope is going to be equal to S epsilon over the square root of the xij's minus x bar j squareds times the 1 minus r squared j. Now, we've talked a little bit about the residual standard deviation. That's our S epsilon, right? And essentially those xij minus x bar j, that's giving you the variability of the xj's, right? Those values are squared, but that's your variability in your xj's. Your r squared j, that is somewhat different than the traditional r squared that you've thought about in the passed. What it actually is, when you have r squared j, this is saying, what is the r squared value obtained by letting the xj be the dependent variable? So essentially, I'm going to regress xj on x1 plus all the way down to xj minus 1. And then I'm going to skip xj and I'm going to do xj plus 1 all the way up to xk. So when I do this regression of the xj, right, I'm going to then be able to calculate the r squared value where xj is the response variable. And that is going to measure the dependence of the xj on the other variables. Okay, so just a quick note, if you want to calculate x bar j, how would we actually do this? All right, what we're doing is we're going to sum up over all the I people. So let's think about the first variable, xi1, right? xi1 is going to be, for the first variable, that's x11, x21, all the way down to xn1, right? If you wanted xij, that's going to be x1j, x2j, all the way up to xnj, right? So essentially, that's saying for the jth variable, give me all the values for each of the people in my study. That's going to give me my xij variables. All right, so when we sum up the x1j's all the way down to the xnj's, and we divide by our sample size, that's going to give us the mean value of x bar j. Okay, so from there, we should have all the pieces, because remember, once you have the distribution of some variable, what can we do from here? We can calculate confidence intervals and we can do hypothesis tests. So at the end of the day, we're going to be asking ourselves, we have a particular value of beta hat j, but what is a reasonable confidence interval for beta j given what I saw with beta hat j? And also, is there a relationship between x, j, and y? So is there a positive or a negative slope? Is the true slope positive or negative? Okay, so we're going to be doing those in the following videos. Look forward to seeing you.